Welcome! In this session, we'll tackle a popular problem, number 896 monotonic array. Together, we'll explore its key concepts, break down approaches step by step, and analyze their complexity. Let's dive in. In this problem, we are dealing with the concept of a monotonic array. An array is considered monotonic if it is either monotone increasing or monotone decreasing. Now, what do these terms mean? If an array is monotone increasing, it means that for every pair of indices I and j where I is less than or equal to j, the value at nums, I, is less than or equal to the value at nums, j. On the other hand, an array is monotone decreasing if, for all such pairs, nums, I, is greater than or equal to nums, j. Your task is to determine if a given integer array is monotonic and return true if it is, or false if it is not. The input will be an integer array, and the output will be a Boolean value that reflects whether the array is monotonic. Let's look at some examples to better understand this definition. In the first example, the input array is 1, 2, 2, 3. The output is true because the array is monotone increasing. This is clear because for every pair of indices I and j where I is less than or equal to j, the condition nums, I, equals nums, j, holds true. For instance, 1 equals 2, 2 equals 2, and so on. Now consider the second example, where the input is 6, 5, 4, 4. Here, the output is also true, but this time it's because the array is monotone decreasing. All elements satisfy the condition nums, I, equals nums, j, for I equals j. For example, 6 equals 5, 5 equals 4, and so on. So, both arrays meet the criteria for being monotonic, just in different ways. Now let's examine the third example. The input array is 1, 3, 2, and the output is false. Why is that? It's because this array does not consistently follow either the rules for monotone increasing or monotone decreasing. While 1, 3, which initially suggests an increasing sequence, the next comparison 3, 2 breaks that pattern. This inconsistency means the array is not monotonic. Moving to the fourth example, the input is 1, 2, 4, 5, 5, 6. Here, the output is true, as the array satisfies the condition for monotone increasing. Every pair of elements follows the rule nums, I, equals nums, j, even when there are repeated values like 5 and 5. Arrays like these, where elements never decrease, are valid monotonic arrays. In the fifth and final example, the input array is 9, 9, 9, 9, and the output is true. This array is a special case because all the elements are the same. Since there's no increase or decrease between any elements, it satisfies both the conditions for monotone increasing and monotone decreasing. Arrays where all elements are identical can always be considered monotonic. With these examples, the problem statement becomes clear. You need to check if an array maintains a consistent pattern, either increasing or decreasing, throughout its length. Now, let's consider the constraints and edge cases you might encounter. The array length can range from 1 up to 10⁻⁵, and the values in the array can be as small as -10⁻⁵ or as large as 10⁻⁵. For edge cases, a single element array, like 7, is always monotonic, as there are no comparisons to be made. Arrays with all identical elements, such as 3, 3, 3, are also monotonic because they satisfy both increasing and decreasing conditions. On the other hand, arrays with mixed order, like 1, 3, 2, are not monotonic. It's important to ensure your solution handles large arrays efficiently to meet the constraints. Finally, strictly increasing or strictly decreasing arrays, such as 1, 2, 3, 4, or 10, 9, 8, 7, are straightforward examples of monotonic arrays. These considerations will help you design a robust and efficient solution for this problem. To begin, let's explore the brute force approach. The intuition here is straightforward. We check every possible pair of elements in the array to determine whether the monotonicity conditions are satisfied. For a monotone increasing array, each earlier element should be less than or equal to every later element. Similarly, for a monotone decreasing array, each earlier element should be greater than or equal to every later element. The algorithm uses nested loops to compare all pairs of elements, verifying these conditions. While this method is simple and easy to implement, it comes with significant drawbacks. The time complexity is O(n squared) due to the double iteration, and this makes it highly inefficient for larger arrays. Additionally, it doesn't take advantage of the sequential nature of the array, which means we're performing a lot of redundant comparisons. Though it works, it's not practical for most real-world scenarios. Now, let's consider an optimized single-pass approach. Instead of comparing all pairs of elements, we can determine the monotonicity by analyzing adjacent elements and tracking trends. The key here is to check if the array is consistently increasing or decreasing. As we traverse the array, we use two flags, one to indicate if the array is increasing and another to indicate if it's decreasing. If we find that adjacent elements follow an upward trend, we set the increasing flag. Conversely, if they follow a downward trend, we set the decreasing flag. If both flags are set to true during the traversal, we know the array is not monotonic. This approach is much more efficient with an O(n) time complexity, as we only traverse the array once. Moreover, it doesn't require any additional space, making it scalable and well-suited for larger arrays. However, care must be taken to handle edge cases, such as arrays with all identical elements, where no clear trend is established. Alternatively, we can use a two-pass approach to solve this problem. This method breaks the problem into two separate checks, one for monotone increasing and one for monotone decreasing. During the first pass, we verify if every element is less than or equal to the next. If this holds true for the entire array, it's monotone increasing. In the second pass, we check if every element is greater than or equal to the next, which would confirm monotone decreasing. If either condition is satisfied, the array is monotonic. The time complexity remains O(n) as we traverse the array twice, and the space complexity is O(1) since no additional space is used. While this method is conceptually simpler and may be easier to implement for some, it performs redundant checks. For instance, if the array is already determined to be increasing, the second pass to check for decreasing is unnecessary. Thus, while effective, it's not as efficient as the single-pass approach. After evaluating the options, we've chosen the single-pass approach as the optimal strategy. The key insight here is that we can determine the array's monotonicity by analyzing adjacent elements in a single traversal. This method eliminates redundant comparisons by dynamically detecting trends as we iterate. The aha moment comes from the realization that comparing every pair of elements is unnecessary when the array's sequential nature allows for trend detection in just one pass. This makes the algorithm both efficient and scalable, with a time complexity of O(n) and minimal space requirements. Compared to the brute force approach, which is prohibitively slow for large inputs, the single-pass approach is much faster. While the two-pass method is also linear in time, it involves unnecessary work when monotonicity can be determined earlier in the process. The single-pass approach strikes the perfect balance between simplicity and performance, making it the best choice for solving this problem. In conclusion, the single-pass approach is the clear winner for this problem. It provides an elegant solution that combines efficiency and simplicity, ensuring optimal performance even for large arrays. By leveraging the sequential nature of the array, it avoids redundant computations and handles all relevant edge cases effectively. This balance makes it the most practical and scalable solution, aligning well with the requirements of this problem. To determine if an array is monotonic, we first need to understand the concept of monotonicity. An array is monotonic if it is either entirely non-increasing or non-decreasing. This means, in a monotone increasing array, for every pair of indices where the earlier index is smaller, the value at that earlier index must also be less than or equal to the value at the later index. Similarly, in a monotone decreasing array, for every pair of indices, the earlier value must be greater than or equal to the later value. To check for monotonicity, we can use a brute force approach by iterating through all possible pairs of indices in the array and evaluating their relationships. Specifically, we use two nested loops. The outer loop starts at the first element and goes up to the second to last, while the inner loop begins just after the current outer loop index and continues to the end of the array. For every pair, we check if the values indicate non-increasing or non-decreasing behavior, and we use flags to track these conditions. During this process, we maintain two Boolean flags, one to track if the array is monotone increasing and another to track if it is monotone decreasing. Both flags are initially set to true, assuming the array could be either. As we iterate through the pairs, if we find any instance where the earlier value is greater than the later value, we invalidate the monotone increasing condition by setting the corresponding flag to false. Similarly, if we find an earlier value smaller than the later value, we invalidate the monotone decreasing condition. If both flags become false during the iteration, we can terminate the loops early since the array is neither non-increasing nor non-decreasing, and thus, it cannot be monotonic. After completing all iterations, if at least one of the flags remains true, the array is monotonic, and we return true. Otherwise, we return false. While this approach guarantees correctness, it is computationally expensive as it requires checking all pairs of elements, leading to a time complexity of O(n)². This inefficiency becomes significant as the array size increases, making it necessary to explore optimization opportunities. For example, we can recognize that instead of comparing all pairs, checking consecutive elements in a single pass is sufficient to determine monotonicity. Additionally, edge cases such as empty arrays or arrays with a single element are trivially monotonic, and arrays with identical elements are both non-increasing and non-decreasing. The brute force algorithm primarily relies on the input array itself and the two Boolean flags for tracking monotonicity. These flags, is_increasing and is_decreasing, allow us to efficiently terminate early if the array is found to be non-monotonic. With these minimal requirements, the approach avoids the need for additional data structures. The algorithm starts by handling edge cases. If the array is empty or has only one element, it's immediately considered monotonic. Then, using nested loops, we compare each pair of elements in the array. If the earlier value is greater than the later value, we set the is_increasing flag to false, as it violates the increasing condition. Conversely, if the earlier value is smaller than the later one, the is_decreasing flag is set to false. Should both flags become false at any point, we terminate early, returning false since the array is confirmed to be non-monotonic. By the end of the loops, if at least one flag remains true, the array is monotonic, and we return true. While this method is straightforward, its inefficiency lies in the O(n)² time complexity, as every pair of elements is compared. This is demonstrated in the Python implementation, where we check all pairs and use the flags to track violations of monotonicity. Finally, the algorithm concludes by returning whether either the is_increasing or is_decreasing flag remains true, indicating monotonicity. However, as we analyze the brute force approach, we find that its O(n)² time complexity makes it impractical for larger inputs. The nested loops are the primary culprit, as they require comparing every possible pair of elements. On the other hand, the space complexity is efficient at O(1), since only two flags are used. To improve upon this, we can consider an optimized approach that eliminates the need for nested loops. By traversing the array once and comparing only consecutive elements, we can achieve a time complexity of O(n). During this single pass, we maintain the same two flags, one for increasing and one for decreasing monotonicity. If any consecutive pair violates a condition, we update the corresponding flag. If both flags become invalidated, we return false immediately. Otherwise, if the loop completes without invalidating both flags, we know the array is monotonic and return true. This optimized approach not only reduces the computational cost but also simplifies the logic, making it more efficient and scalable for larger arrays. This solution determines whether an array is monotonic using a single traversal. The function isMonotonic takes the input array nums as an argument. First, two Boolean flags, increasing and decreasing, are initialized to true. These flags are used to track whether the array remains monotonic in either increasing or decreasing order. The function then iterates through the array starting from the second element, index 1. For each pair of consecutive elements, it checks if the current element is greater than the previous one. If so, the decreasing flag is set to false since the array violates decreasing order. Similarly, if the current element is smaller than the previous one, the increasing flag is set to false as it violates increasing order. During the iteration, if both flags become false, it means the array is neither entirely non-decreasing nor non-increasing, so the function immediately returns false. If the loop completes without both flags being false, the array is monotonic. The function returns true as either the increasing or decreasing flag, or both, remains true. This approach is efficient with a time complexity of O(n), where n is the length of the array, because it only requires a single traversal. The space complexity is O(1), since no additional data structures are used. This is the Java implementation of the monotonic array problem. The logic mirrors the Python solution, using two flags, increasing and decreasing, to check the array's monotonicity. The method iterates through the array, comparing adjacent elements to update the flags. If both flags become false, the method returns false immediately. If either flag remains true after the loop, the array is monotonic. Key differences include Java's use of explicit type declarations and the absence of Python-specific syntax like elif. This implementation adheres to Java conventions and ensures clarity and efficiency. The problem is to determine if a given array, nums, is monotonic. An array is monotonic if it is either entirely non-decreasing or non-increasing. For non-decreasing arrays, each element is less than or equal to the next, while for non-increasing arrays, every element is greater than or equal to the next. Let's consider the example where nums is 1, 2, 2, 3. Initially, we assumed the array could be both increasing and decreasing, so we set two flags, increasing equals true and decreasing equals true. In the first iteration, we compare nums 1, 2 with nums 0, 1. Since 2 is greater than 1, this violates the condition for a non-increasing array, so we update decreasing to false. However, the increasing flag remains true, as the non-decreasing condition is still valid. In the second iteration, we compare nums 2, 2 with nums 1, 2. Since the values are equal, neither condition is violated, so both flags remain unchanged. In the third iteration, we compare nums 3, 3 with nums 2, 2. Again, since 3 is greater than 2, this continues to violate the non-increasing condition, but decreasing is already false, so it remains unchanged. The increasing flag, however, is still valid. At the end of all iterations, we check the flags. Since increasing is still true, the array is monotonic, and the function would return true. Now, let's explore a second example with nums equals 6, 5, 4, 4. Again, we start with increasing equals true and decreasing equals true. In the first iteration, we compare nums 1, 5 with nums 0, 6. Here, 5 is less than 6, which violates the condition for a non-decreasing array. Therefore, we set increasing to false, but the decreasing flag remains valid. Next, in the second iteration, we compare nums 2, 4 with nums 1, 5. Since 4 is less than 5, this continues to violate the non-decreasing condition. However, increasing is already false, so there's no further change to that flag. The decreasing flag remains valid, as the array is still adhering to the non-increasing condition. In the third iteration, we compare nums 3, 4 with nums 2, 4. Since the values are equal, neither condition is violated, so both flags remain unchanged. At the end of the iterations, since decreasing is still true, the array is monotonic, and the function would return true in this case as well. Now, let's consider a third example where nums equals 1, 3, 2. Again, we initialize increasing equals true and decreasing equals true. In the first iteration, we compare nums 1, 3 with nums 0, 1. Since 3 is greater than 1, the array violates the non-increasing condition, so we set decreasing equals false. The increasing flag remains valid at this point. In the second iteration, we compare nums 2, 2 with nums 1, 3. Here, 2 is less than 3, which violates the non-decreasing condition. As a result, we set increasing equals false. At this point, both flags are now false, indicating that the array is neither non-decreasing nor non-increasing. Therefore, the array is not monotonic, and the function would return false. This approach is efficient because it only requires a single pass through the array, resulting in an O(n) time complexity. The use of two flags, increasing and decreasing, allows us to track whether the array violates monotonic conditions as we iterate. If both flags are set to false at any point, we can immediately determine that the array is not monotonic. This solution also handles edge cases effectively, such as arrays with only one element or arrays where all elements are identical. These cases are inherently monotonic, as there are no comparisons that can violate the conditions. Overall, this algorithm provides a simple yet robust way to determine the monotonicity of an array. Here, we analyze the time complexity of the solution. The overall complexity is O(n), where n is the number of elements in the input array, nums. This is primarily due to the single iteration over the array. First, we initialize two Boolean flags, increasing and decreasing, which are set to true. These operations are performed in constant time, contributing 1. Next, the for loop iterates over the array, starting from index 1 to the end, performing n1 iterations. Each iteration involves constant time comparisons and updates to the flags, so the total contribution of the loop is n1, which simplifies to n. Additionally, there is an early exit condition where the loop may terminate early if both flags become false, but this does not affect the overall asymptotic complexity, which remains n. Finally, the return statement checks whether either of the flags is true, and since this is a constant time operation, it contributes 1. Combining all these steps, the dominant term is the iteration, so the time complexity is n. Now let's examine the space complexity. The space complexity of this solution is 1, as it does not require any additional memory that grows with the size of the input. The algorithm uses the input array nums but does not create any new data structures proportional to the input size. This ensures that the input array itself does not contribute to the space complexity. Additionally, the solution utilizes two Boolean flags, increasing and decreasing, and a loop index variable I. These are all simple variables that require a fixed amount of space, regardless of the size of the input array. Since no other memory is allocated, the space complexity is dominated by these constant space requirements, resulting in a space complexity of 1. Let's compare this optimized solution with a more naive approach. A naive solution would check the monotonicity of the array in two separate passes. In the first pass, it would verify if the array is entirely non-decreasing, and in the second pass, it would check if the array is entirely non-increasing. Each of these passes takes n time, so the total time complexity is n plus n, or simply n. However, this approach is inefficient because it performs redundant checks and does not terminate early when both monotonicity conditions fail. The current optimized solution improves upon this by combining both checks into a single loop. This eliminates redundant computations while maintaining the same asymptotic time complexity of n. To prove this big O complexity, note that the loop iterates at most n1 times, and each iteration involves constant time operations. This makes the time complexity proportional to n. Furthermore, no additional data structures are used, and only constant space is allocated for the flags and loop index, solidifying the space complexity at 1. Thus, the final time complexity of the solution is n, while the space complexity is 1. Now, let's consider the best, average, and worst cases for this algorithm. In the best case, the input array is already monotonic, either completely non-decreasing or non-increasing. Here, the loop may terminate early as the monotonicity is verified quickly, but the asymptotic complexity remains n. In the average case, the array contains a mix of increasing and decreasing sequences. This requires the algorithm to perform a full pass over the array, resulting in n time complexity. Finally, in the worst case, the array alternates between increasing and decreasing multiple times, forcing the loop to iterate through the entire array. However, even in this scenario, the time complexity remains n. To summarize, the optimized solution achieves n time and 1 space complexity and improves efficiency by combining checks into a single loop, reducing redundant computations compared to the naive approach. When working on the monotonic array problem, it's important to be aware of some common mistakes that can trip you up. One of the most frequent issues is not handling edge cases properly. For example, arrays that are empty or contain just one element are inherently monotonic, yet neglecting to account for them can lead to unexpected errors, such as out-of-bounds indexing or incorrect outputs. Another mistake is assuming the array has a fixed direction, like always increasing or always decreasing, without first verifying the trend dynamically. This could lead to failure in cases like 1, 2, 1, or 3, 3, 2, where the trend isn't consistent from the start. Efficiency is another key consideration. Using nested loops to compare elements results in an n squared solution, which works but is inefficient for larger inputs and often penalized in interviews. Instead, aim for n approaches. It's also crucial to note that the problem does not require the array to be strictly monotonic. Equal elements are allowed. For instance, arrays like 1, 1, 2, 2 are valid monotonic arrays, and overlooking this detail could result in incorrect outputs. Lastly, avoid overcomplicating your logic. Using multiple nested if-else blocks for conditions can make your code harder to debug. A simpler approach, such as using flags or clean comparisons, is both more readable and less prone to errors. Now, let's talk about what this problem often tests in interviews and how you can approach it effectively. First, the monotonic array problem is designed to assess your ability to implement simple logic efficiently. Interviewers want to see if you can handle edge cases and write clean, concise code. Efficiency is key here. Most array traversal problems, including this one, should aim for O(n) solutions. However, it's worth noting that interviewers may start by asking for a brute force solution to gauge your thought process. They will then expect you to optimize it, so be ready to highlight the trade-offs between simplicity and efficiency. You should also prepare for possible variations of the problem. For example, you might be asked to check for strictly monotonic arrays or to modify the array minimally to make it monotonic. Both require a clear understanding of the core logic. Communication is another critical aspect. Be sure to articulate your thought process step by step. Discussing how you determine the direction of monotonicity or how you handle edge cases can demonstrate your problem-solving skills effectively. Lastly, this problem is related to others in the same category, like non-decreasing array, valid mountain array, and wiggle subsequence. Understanding these variations can help you recognize patterns and prepare for similar challenges. Finally, let's explore some alternative approaches to solving the monotonic array problem. One of the most efficient methods is the single-pass approach using flags. Here, you maintain two flags, is increasing and is decreasing, to track the monotonicity of the array as you traverse it. By updating these flags based on comparisons, you can determine the result in O(n) time with O(1) space complexity. This method is both clear and efficient, though it might be slightly harder to debug compared to simpler conditional checks. Another useful strategy is the two-pointer technique. With this approach, you use two pointers to dynamically compare adjacent elements, which can simplify handling certain edge cases. Like the single-pass method, this runs in O(n) time with O(1) space, although careful attention is needed to handle scenarios such as when the pointers meet. Lastly, there's the brute force approach, which involves comparing all pairs of elements where the first index is less than the second. While this method is straightforward to implement, it has a time complexity of O(n squared, making it unsuitable for large arrays. While useful for understanding the problem, brute force is rarely the optimal choice. Each of these approaches has its own trade-offs, so it's important to choose the right one based on the problem's constraints and requirements. Great job! We summarized the problem, reviewed the approach, and discussed takeaways. Stay curious, keep improving, and we'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!